Hey kiddos, here's the spiral review for spiral 10, starting with implicit differentiation logs. Here we're given a function that already has derivative as part of it, and they're asking us for the second derivative at the point 3, 0. Okay. So the first thing I probably should do is to maybe think about this. I know I see a product rule here. That's a big deal. That side's okay. And maybe go about taking the derivative. All right, product rule is the first. So x plus 2y times the derivative of the second. Derivative of the first derivative would be the second derivative, which we write as d squared y over dx squared. You could also write that as y double prime. And then that's going to be plus the derivative of the first. So 1 plus 2y. I'm going to keep this in this notation, so dy dx. That shouldn't be a y, sorry. And that's going to be times dy dx. That's interesting. And then on the other side, that's a little bit easier. We're going to have 2 and minus dy dx. Okay, I can plug some stuff in. The problem is I've got an x and a y, but I also have dy dx's in here. I don't really know what dy dx is at this point. Oh, but I could plug it into the original equation. I'm going to rewrite this over here, but instead I'm going to plug in the point 3, 0. So that would be 3 plus 0 is just 3. dy dx, and that's going to be equal to 3 times 2 is 6, and minus 0 would just be 6, okay? That means that dy dx is equal to 2. So now when I plug stuff in over here, we've got 3. The 0 part goes away. This is the second derivative. I'm just going to write that as y double prime. These mean the same thing, but it's less for me to write. And then we've got plus 1 plus 2. We said dy dx was 2. And we said dy dx was 2. And over here we've got 2 minus 2, which is 0. That's kind of cool. Okay, so 3y double prime plus, that's going to be 5 times 2 is 10. And that's equals to 0. Negative 10 over 3 is what I'm getting, which is going to be a. Moving on to 18. I know they're asking me for the derivative. I might as well just start trying to take the derivative, although I really don't want to do an ln thing if I don't have to. It might be nice to convert this, but in looking at this, I don't see any e's in my answers, so I'm wondering if I should just kind of leave it like this and just see where that goes. Okay, so the derivative of ln of stuff is 1 over that stuff. So 1 over 2x plus y, and then times the derivative of that stuff, which is 2 plus y prime. Okay? Derivative of x is 1, derivative of 1 is 0, so we're done with that part. Nice. I also noticed that I got something in terms of a fraction. If I multiply both sides by 2x plus y, that'll get rid of my fraction, and I like that. So that would give me 2 plus y prime is equal to 2x plus y, and y prime is equal to 2x plus y minus 2, which happens to be b. I feel like I've done that problem before. I wonder if that was on a previous review and I just didn't realize it. Okay. For number 13, we've got a function. We're asked to find the derivative of that function of ln of x. So I guess I could take a look at this. This is going to be a chain rule problem. I might plug in first. I don't know if this is the best option, but this is an option. So you've got ln of x squared plus 2 ln of x. The derivative of ln of x squared would be 2 ln of x to the first multiplied by the derivative of ln of x, which is just 1 over x. And the derivative of 2 ln of x would be 2 over x. Okay, these both have the same denominator, so I could write this as 2 ln of x times 1, okay, and then plus 2, all over x, and that happens to be choice A. Alright, so we've got a graph of e to the tangent of x. Ooh, I'm spinning this the wrong way and I'm losing it. Minus 2 crosses the x-axis at one point in the interval between 0 and 1. Alright, so the first thing I've got to do is use some kind of calculator to figure out what this is. If you're using a TI calculator, you can do this in terms of e to the tan x minus 2 is y1, and you're going to use second calc 0 to be able to zero in on that, no pun intended. Another option would be to use y1 is equal to e to the tangent of x, and y2 is equal to 2, because if you were to set this equal to 0, you could make e to the tan x equals 2. And that might be an easier thing for you to do, and then instead you'd be using second calc intersect. Either way, when we do this, we get something like x is equal to 0.606. I did this on Desmos. It doesn't give me an extra decimal place, but on the calculator, it'd be nice to have 4, just so you don't lose track of that. And then it asks, what is the slope of this graph at this point? In other words, if we took the derivative of this and then plugged this point in, what would we get? On your calculator, if you go under the math menu, I'm not going to be able to fit the word math in. Oh, that's not too bad, actually. What you can actually do is to take the derivative with respect to this. So there's going to be a ddx function. You want to put an x there. And in here you can do e to the tan x minus 2, and it's going to give you an option of x equals, and you want to put in 0.606. If you've got a TI-83 or older, which hopefully there aren't many that have that, it's going to be n-deriv. It's called a numerical derivative. And what you're going to have to do is e caret tan x in parentheses minus 2, comma, 0.6, actually it's comma x to tell you what variable you're using, and comma 0.606. We're going to go more into these after our break because we're going to revisit some of the concepts that we've seen, but have some more calculator active stuff for that. In either case here, the derivative, and I'm going to kind of shortcut this on the computer using Desmos, and I get 2.9599. Which that's only using 3 decimal places. That's closest to this one. On a calculator, you're going to be able to get an exact value with more places. Next up, we've got some integrals, area, and RAM stuff. For the first problem, we're talking about the integral of e to the x squared dx, and it's approximated using 2 inscribed rectangles of equal width, and then approximate the trapezoidal roll with n equals 2. Oh boy. I have no idea what this thing looks like, but what I'm going to do is make a pretend graph. I'm going to plug in some values because I know if I have 2 rectangles, I'm going to need some points here. So at 0, e to the 0 would be 1. At 1, e to the 1 would be e. And at 2, e to the 4 would be e to the 4. Again, no idea what this curve looks like, but I'm going to pretend it looks like this. And we're trying to take a look at either the rectangles or the trapezoids that come in here. I've already kind of drawn a picture that's really nice for trapezoids, so what I might do is do that one first. And when setting up a trapezoidal approximation, we're going to have one trapezoid here, one trapezoid here. Each one would have a width of 1, because this is going from 0 to 1, and this is going from 1 to 2. So the trapezoidal approximation would be a half times base 1 would be 1, base 2 would be e, and then a width of 1. And then a half, base 1 would be e, don't mind the bell, base 2 would be e to the 4th, and then times a width of 1. You got a calculator to do this, that's totally fine. We'll take a look at the rectangles next. Okay, continuing looking at rectangles. One of the things you can't really tell in my bad drawing is that this thing is gradually going up because e is higher than 1 and e to the 4 is much higher than e. So if we're looking at rectangles with equal width, these are still dealing with bases of 1. But this time we've got inscribed heights. That just means that we're going within the curve or under the curve, and that happens to be left rectangles for this graph. And the first height would be at 1, the second height would be at e. Okay, so rectangles would have a height of, or an area of 1 plus e. And my trapezoids are going to have a much more pleasant thing, and that's going to be whatever this delightful thing is. Trapezoidal sum is going to be 30.517. I can't do a 7, that came out as a 2, that's fun. And 1 plus e is going to be about 3.7, sorry, I got distracted there, 18. Okay, when I subtract those, I get a difference of 26.799, which is going to be 26.8. Looking at the next problem, so we got a left Riemann sum, a right Riemann sum, and a trapezoidal sum, which I use to approximate this. And the graph is shown here, which gives an underestimate of this. Okay, so let's just talk about each of these. So I'm just going to make two intervals just so we can see the shapes of this pretty well. And a left Riemann sum I'm going to do in black. So from here, that would be these two rectangles. Left Riemann sum is definitely an underestimate. Okay. Then we've got a right sum I'm going to do in red. So that would be these two. That's definitely an overestimate, so that can't be it. And then finally, we're going to look at the trapezoidal sum, and that would be connecting these endpoints. First one's really a triangle. Then we got, so I didn't use different colors for that. Trapezoid, there we go, blue. And since both of those are under the actual graph, this one works, so that means 1 and 3 are our answers. The goal here is to decide when this equals the exact area, which of these fit the description that we have. So you got to be a little bit careful as far as paying attention to underestimate and paying attention to each of these pieces. Next up, we got to do some integral properties in FTC. First thing we're being asked to find is the derivative of an integral. That sounds like FTC to me. And what we're being asked here is to take the derivative with respect to x of the integral from 4 to 2x of the square root of t squared minus t dt, and then plug in 2. So we're going to start by the derivative. We know with FTC that I can take this value, plug it into each of these, so that's going to be the square root of 2x squared minus 2x. since the bottom is a number, that's going to be 0 when I take the derivative. And I know I've got to multiply by the derivative of this, which is just 2. When I plug in 2, we're going to get the square root of 2 times 2 is 4. 4 squared is going to be 16. And minus 2 times 2 is 4. And then times 2. 16 minus 4 is going to be square root of 12. And then we got times 2. That gives us e. For the problem labeled 78, we've got an explanation that the area under the curve from 1 to 3, okay, so that's this part here, is going to be 2.3. And it asks us about f of 3 minus f of 0. And this notation tells us that this is the antiderivative of f of x. This graph is f of x. So this is saying the antiderivative at 3 minus the antiderivative at 0. In other words, we're going from 0 to 3 of the derivative function. And what that really means, we're finding the area from 0 to 3. The good news is we already know part of this. This part here is 2.3. That's why they told us this. And here we've got a 1 by 2 rectangle that has an area of 2. 2 plus 2.3 is going to be 4.3. For number 3, the first thing I'm going to do is to rewrite this as the integral from 1 to 2 of x to the negative 2 dx. I really don't want to try to even deal with these as fractions. We don't have a way to go backwards from the quotient rule, so we really do have to rewrite this as something we can power rule. I'm going to use the inverse power rule, and when I do that, we're going to get x to the negative 1. I'm going to add 1, dividing by negative 1. That's going to be evaluated at 2 and at 1. So that's really negative 1 over x. So negative 1 over 2 minus negative 1 over 1. So that would be negative a half minus minus is plus, which equals just a half. And finally, we move on to some substitution in differential equations. Substitution, we're going to start off with, as a hint, in the section you're probably going to have to use substitution. I've got a messy function here. I know that whenever I've got something in an exponent, that's going to end up being my u. So let's start with that. U is equal to x cubed. That means that du dx is going to be 3x squared, and that means that dx is going to be du over 3x squared. So when I go to substitute this stuff in, we end up with x squared on top, e to the u on the bottom. I don't love that, and we're going to talk about that in a second. And then we've got a dx over here. I'm actually going to take a step back because I don't love the way this is setting up. It's not going to end up with something that I like because I don't see a clean antiderivative here. And what I'm going to do is, before I even begin this, rewrite this all in a line. So that would be x squared times e to the negative x cubed. What that's going to let us do is to rewrite this as negative x cubed for u, which means we got negative 3x squared in both parts of this. And instead of what we had there, we end up with x squared e to the positive u du, but now we're all kind of lined up in a row. And that's going to be du over negative 3x squared. What I like about this is that I don't have to deal with that being on the bottom of a fraction, and I can just kind of go straight forward at this. So the x squareds cancel. I can bring that negative 3 out front as negative a third because it's on the bottom. And we know that the antiderivative of e to the u is just e to the u. So we get negative a third e to the u plus c. To finish this off, let's put that x back in here, and that would end up being negative a third e to the negative x cubed plus c. And I don't really see that up here, but I've got one here that looks really close to it. In fact, the only thing that's different here is that that e to the positive x cubed is in the bottom. Oh, they did the same thing that we did in order to make this a little bit easier to solve. They put the negative exponent on the bottom with this thing and made it a positive exponent. And that's it. For number 21, we're being asked to use what's called separation of variables to solve a differential equation. We've got dy dt. K is a constant. That means it's just a number. We can kind of just deal with that. We're going to separate our variables onto both sides. And in doing that, it's going to look like dy is equal to ky dt. And then to get the y back with the dy, I'm going to divide both sides by y. And I'm going to write this as 1 over y. dy is equal to k, again, that's just a constant, dt. The antiderivative of both sides. And the antiderivative of 1 over y is going to be ln of the absolute value of y. And for the other side, the antiderivative of a constant, if this was the antiderivative of 2 dx, we'd have 2x plus c. Because this is just a weird constant like k, it's going to be k, and now we're going to do t. And don't forget that plus c at the end of the problem. You need to have that. Okay, none of these look quite like this. In fact, they all seem to have e's in them. So what we can do is to convert this to exponential. So this is going to be y is equal to e to the kt plus c. And it's still going to be the absolute value, but that means we could have either a positive or negative version of what is on the right side. And if I look here, this one has a y in the exponent. Not going to happen. This one looks not quite like this, but it doesn't have anything that I know would exclude it. Same with this guy. That one doesn't look anything like that. That one doesn't look anything like that either. So what we got to figure out is how we can get to an answer that looks like one of these two. And the way we're going to do that is with exponent rules. I also notice both of these are the positive, so I can kind of forget about my absolute value for now. I could rewrite this as e to the kt times e to the c. And I can do that because of exponent rules. And then finally, e to the c is just a constant. So I'm just going to call this, I don't know, I already have a k, I already have a c. Let's call this constant d, just because it's the next letter, and make this e to the kt. A lot of times we just use another c here, and just say it's a different constant than we had up here. So if I look here, I've got e to the kt times some constant. That constant could be any number, depending on what the problem has, so it could even be 2. What this doesn't have is something added at the end of this, which means that that can't work either.